thanks all for coming. I'll be telling you all about how we made a CouchDB installation a lot faster than how we found it for, at the time, very important situation for our customer. My name is Lehnardt. I'm a CEO at Neighborhoody Software. I'm also the PMC chair for Apache CouchDB and Apache PouchDB. I've been doing computers since 1988. I've been on the web since 1998. And my day job is designing, building, maintaining large-scale database systems. Again, thank you for having me. I forgot 15 years ago, I think, Isabel, Simon, and I started this conference. I have for a long time not been involved with this. I really love what everybody has done with the place. I love that it's so successful that I can come back every year and see that there's new buzzwords to be talked about. So it's very nice that I can be here today. Thanks again all for coming. All software benchmarks and claims of performance are carefully crafted lies. This talk is no different. Instead of giving you a quick do these 1, 2, 3 steps, so you get a magic speed up, I'm to explain how my team and I arrived at the changes that we made and how we rigorously tested those changes to make sure we understand their impact. All of this is to give you the tools to follow the process yourself, at the end of which you may come to very different conclusions than we had because your system is different than what we had to deal with. But I want to show you our journey so you can go on your own journey for this. So let's get started. My company offers professional services for Apache CouchDB. One of these services is production support. And we had a customer that has been using CouchDB for over 10 years for a AAA sports game. I cannot tell you which one. It's one of the big ones. It's not the biggest one. And draw conclusions as you see fit. When they were ready to launch their newest edition, they came to us with the following situation. They had a setup of a 6-node CouchDB cluster hosted on AWS EC2. Each of the nodes in the cluster had 192 CPU cores, 768 gigabytes of RAM, NVMe storage, like all the good stuff. The way they work is they set up a cluster for one of the iterations of the game each. So they had a cluster for all the previous games each. And now, latest version came out last year, they set up a new cluster. So they had some background where they knew, okay, this amount of hardware gives us this much performance roughly. The thing, that's what that looks like in the end. However, when they ran their benchmarks on this, they only saw about a 2x increase in requests per second for what they were measuring there. They were expecting at least 3x, because that's how much bigger the individual nodes were in terms of CPU and RAM. But they expected even more because they added a whole other node. The previous versions only had 5-node clusters. So in addition to having not as many requests per second as expected, they saw a 10x increase in request latency while running the benchmark, and that's neither expected nor desirable. While their benchmark reflected a worst-case scenario in total of number of requests and request concurrency, and the median case that they were expecting what the game would end up using was fine, the results they saw were not satisfactory, and that's where we got called in to see if we can look at the scenario, see if we can get more requests per second out of the setup, and if we can get the 10x latency spike under control as well. So with these goals in sight, we started going. And we'll have to start with the benchmark. It was a really, really bad benchmark. It's fine, because it's a benchmark the customer came up with. We looked at it, and we're fine with when the customer doesn't do the optimal thing if they do something that gets the job done in the end. We're not judging them. But why was this benchmark bad? Well, it tested things in a way that played against the strength of CouchDB. So they knew their actual application would never be treating CouchDB this badly, but if they made their cluster perform in the way that they wanted, they would know they had enough excess capacity to host the game properly. This wasn't the kind of benchmark where we're trying to most adequately model the client application behavior. That takes a lot of time to get right. Instead, this benchmark takes a couple of minutes to set up, and it was entirely satisfactory to solve the problem that we had. So it's this is one of those, the perfect is the enemy of good situations where something that's really basic actually is good enough for the thing that you need to be doing. Some of you who have been in the game a little longer will say that you haven't heard this name in a long while. The benchmark tool that the customer chose was AB, Apache Bench. It's a tiny tool that allows you to send the same type of HTTP request and with a defined concurrency as fast as you can, going back and forth. It's a very brute force, very simplistic benchmark, but the tool has been around since the 1990s and does this job very well. So I was fine to do this in this context. And specifically, the benchmark for AB instances were retrieving a specific document from a database, like look up a record in a single database, and then 5 instances were retrieving a dynamic query result, a view result, out of a selection of 4 databases. And then each of the instances would run 1 million requests at a concurrency of 300. So that's where you see this is a really, really bad benchmark. This is not how you benchmark software usually. But it was enough to show that the cluster was not healthy in the way that we needed it to be, and specifically it's not a scientific benchmark. So this is not where we're trying to find a theoretical limit in the performance of CouchDB, but for a specific set of hardware and software, make sure we can optimize, use it the optimal way. And given the prior experience, we expected a lot more requests per second and no latency spikes were to be had. So it's a bad benchmark, but sometimes bad benchmarks are fine. That's enough about the benchmark. This is what CouchDB, before we can dive in, we need to learn a little bit about how CouchDB works on the inside. One concept is called database sharding. Each database in the CouchDB URL space, DB1, DB2, and so on, consists of 1 or more shards. A shard is an individual database file that stores all the data in an append-only B+ tree and is accessed via a single file descriptor. Writes are serialized for safety, and then reads can occur concurrently at the same time. By default, CouchDB splits databases into 2 shards, which is what you're seeing here, 2 shard ranges. And all the data is equally shared among both. As a best practice, CouchDB shards should not exceed 10 gigabytes of data or 10 million documents, depending on what you get there. First, for performance reasons and maintainability reasons. And once you reach those sizes dynamically, you can use a feature called shard splitting to increase the number of shards that you have. So when a request comes into CouchDB for a document, say document A, CouchDB sees this lives on the first shard on the left, on my right side over here, serves the request from here. We have document B lives on the other side, gets served from there. Alternatively, with starting with 2 shards and then splitting them as you grow, you can pre-shard your database. Say you're expecting a lot of data to come in, you can say set a shard level at the creation of the database, and that was what the customer was doing. Their shard size was 60, shard number was 60. So you know they're expecting a lot of data and expecting a lot of concurrent requests to that. Sharding a database has multiple effects. 1, you can store more data than fits on a single node by distributing these shards onto different nodes. 2, you can increase parallel read-write performance, as each shard is limited to the throughput of a single file descriptor. Now the writes are limited through a single CPU core. More shards means more CPU cores can work on more file descriptors in parallel, leading to more throughput in general. The trade-off that enables this point I just mentioned is good for individual doc reads, but the trade-off is that aggregate data reads are penalized. So listing all documents in a database, listing the changes of all documents, or making dynamic view queries will slow down linearly with the number of shards. So in general, sharding is good for increased parallel document performance, but can be detrimental to the query performance. And if you remember, the benchmark was doing both. When the customer demonstrated the behavior to us in a call, our immediate gut reaction was that there was something wrong with the network. Why? For that, we have to go into a little more detail about how CouchDB clustering works. Any of the nodes in a cluster can receive any request. There's no special roles. And we'll try to answer it. Normally, requests come in via a round-robin load balancer, as you've seen earlier. And if a node has the data requested, it will return it. And if not, it will proxy the data from another node and return it back to the client. So the first thing to learn is CouchDB has an external HTTP API. It listens on port 5984 and an internal network called Erlang distribution. CouchDB is built in Erlang that allows the nodes in a cluster to talk to each other very efficiently. So we'll have to look at how these different operations work in a little bit more detail. So reading a document and querying a view, what does actually happen there? So to read a document, we've seen this earlier in an abstract form already. If you read a single document, you need to the document will be mapped into a shard range. For the sake of example, I'm still using two shards here, otherwise the slides wouldn't make any sense to you anymore. And then an internal request is sent to all the copies of that shard range. Wait, copies? I didn't mention any of this. All pieces of data are stored 3 times for redundancy as well. So CouchDB will send an internal request to 3 shard range copies and retrieve the document from those. And the first 2 responses that come up with the same value constitute the same the response value to the outside. This is called a quorum request, if you're familiar with the Dynamo lingo from a while ago. So here you can see we're talking to all the nodes that have the shard range 0 to 7. And then if you read the other document, we talk to all the nodes that have the other shard range. When reading a view request, we don't do quorum reads. We only read 1 copy. We only need to talk to 1 shard, but because it's a range request, it's an aggregate request, we have to talk to all the shards. So here we only talk to 2 nodes, 0, 7, and 8F, so the first 2 nodes, to get, for example, list or a query view, this or list all the databases. So with this different, we can see that a document operation will result in at most 3 internal requests, but a view result will will require at least Q, the number of shards internal requests, 1 for each shard. And now remembering the customer had shard level 60, so there's a lot of internal requests going on. You might deduce from that this might become an issue when we're looking into the benchmark that we were doing. So with lots of requests, internal requests needed for the benchmark, our instinct led us to networking issues right away. Customer took this advice, did some dedicated network benchmarking, so took CouchDB down, just did iperf between the nodes, and they immediately saw, very simply, very sillily, they were capped at 1 gigabytes per second. This comes to them because they set this up on small AWS instances for setup and testing, and then once they want to build out the production cluster to actually do some performance testing and eventually launch the game, they just increased the size of the AWS instances. But at a certain point, the smaller AWS instances have slower networking, the bigger ones have bigger ones, and have more networking, of course. But if you grow them slowly, you will tip over a threshold and you have to enable something extra to get the additional networking performance. So with 1 gigabytes per second limited, that was kind of not so great. But once they flipped that AWS setting, they got up to the expected 25 gigabits per second. That was really nice to see and a very cheap thing to find for us because we basically didn't do any work, but trusted our gut. But when they ran the benchmarks, again, the same observations were still true. So that was the bottleneck, but not the underlying problem that we were looking for, or not the immediate thing that we were looking for. So we were looking for other bottlenecks here. So a little interlude for how to do benchmarking, actually. The goal of benchmarking is finding a limit. The limit is for a combination of software and hardware for a specific load pattern. A lot of things on the hardware side can contribute to such limits, like CPU cycles, available RAM, disk I/O, and network latency and throughput. And our job was to find when CouchDB was going to be running into one of those, into those limits, and see if we can remove it. The only way to make a computer go faster is to have it do fewer things. And there are always fewer things to do to achieve the same results until you hit a theoretical limit. So say you eliminated a networking bottleneck like we just did, but the problem still show. Naturally, there exists another bottleneck, a further bottleneck, that is likely not to be the network, so, and one of the other things. So we'll have to look into those next. Before we started trying to find the next bottleneck, we wanted to learn about how the benchmark affects the system. Since there are two types of requests, again, concurrent document requests and concurrent view requests. And we tried each type in isolation and quickly could see that concurrent document requests were absolutely making no difference whatsoever. This is expected. These were over 700 CPUs running in parallel, over 60 shards times 3. We were expecting a lot of read-write capacity to individual documents, so that was not the problem. Concurrent view requests alone showed the problem as well, so that narrowed our scope. We could focus on this individually, and as you saw earlier, the graph with the image with all the arrows, that was kind of our problem space. But we solved the networking thing, so we're looking for other bottlenecks. And just like a week before this came in, we dealt with a different CouchDB support issue at the company, and that issue ended up being a disk I/O issue, and we still knew from just like having had done it a week ago to figure this out real quick. So that's the thing that we looked at next. So concurrent view requests we're focusing on. There's two ways to look at whether disk I/O is the issue with CouchDB. Number one is I/O weight. It's a standard Unix metric that tells you how much the kernel is waiting for a disk to fulfill an operation. If this is consistently high, your disk can't keep up with the number of requests you're sending to it or reading from it. But in our case, that wasn't it. I/O weight was raising a little bit, but obviously didn't cause any issues. If you use block storage like AWS EBS or equivalent in other clouds, there's other metrics you can pull from these systems. Like on EBS, it's called volume queue length, but it's always the same idea. How much IOPS can I get through the system? That wasn't it. So the other thing that where this could be limiting is how CouchDB is using the disk. And we explained earlier that a single shard is backed by its own file descriptor. It's possible to exhaust how much data you're sending through an individual file descriptor. But there's a very high limit. It's unlikely to be the issue. But there's another step on top of this for CouchDB where a single instance of a couch file process handles access to that file. So now we have to learn about Erlang processes for a second. Another slight detour here. Erlang programs are built around processes that are launched, that run, that exit. Processes can launch other processes, processes can observe other processes, and processes can send and receive messages from other processes. So these processes inside Erlang behave much like operating system processes. In most ways, but one. They're lightweight, as you can start 1 million of them in a second and stop them just as fast. They are what makes Erlang really great at makes Erlang really well suited for building apps that can handle a lot of concurrent requests like CouchDB. Every process in Erlang has got a message inbox that contains all the messages that other processes send to it in sequence, and each message can only be handled one at a time. So if more messages arrive than can be handled, the message inbox grows. And one final piece of the puzzle, an Erlang process runs on a scheduler, and the scheduler is tied to a single CPU core. So whatever happens inside this one process, it can never go faster than a single CPU. So in this scenario, like CPU contention could lead to I/O slowness. But back to the analysis. A message sent to the couch file process could be asking for the contents of a document or a view result row like we have in the benchmark. Now, there's a lot of requests coming in concurrently. There's a chance that there are more requests coming in than the CPU, the file descriptor, or the disk can handle. We've already ruled out the disk with I/O weight. So what's next? We can observe the Erlang message queue length in real time. It's a really cool feature of Erlang. You can SSH into an Erlang virtual machine. then write some Erlang code to inspect what the machine is doing. So writing this code is error prone and tedious, but there's a library, open source library that we bundle with CouchDB called Recon that has a lot of built-ins and built in a way that are safe to use in production, even under very high loads. It's an amazing piece of software. So this all looks probably like gibberish to most people who've never looked at Erlang, but this is how you start Remsch. It tells you a little bit about the parameters it's been started with, the exact versions of the software that are running, and then you get a shell prompt, and in that shell prompt you can type Erlang code, and here we're calling the proc window function on the recon module, and we're looking for the message queue length. We want to have the top 3, and we want to sample the VM for 5 seconds. And then we get results back. Those look not very interesting because these are just from my development machine. But you can see here the 3 rows as response, the process identifier, the number of the message queue length, and all of these are 0 because my dev box wasn't doing anything. But when you run the similar benchmark on the local machine to the one that we saw on the customer, just for showing how that looks, we see a different piece of processes here. The first one we see has a message queue length of 4, but its current function is somewhere deep in the Erlang internals. That doesn't tell us very much. The third one, message queue length 2, also deep in the Erlang bowels. That doesn't help us very much. But the middle one is reading or writing a file. It's using the prim file preadnif function. It has a message queue of 3. So there's requests stacking up, and the message queue can handle it quickly enough. So we found something. That's great. Unfortunately, this is just a demo setup to reflect the customer benchmark well enough so I can show you how this works. And another, unfortunately, is that message queue length in single digits for a brief amount of time is totally fine. Like with IO weight, it can grow a little bit. It should be around 0, but it grows to 1 for a second is fine. So this doesn't show us any actual bottlenecks. This is just to show you some cool stuff, what you can do with Erlang to really get into the weeds with performance tuning here. And finally, on our customer systems, that's why I'm showing you this, it just looked the same. Whatever we did, we couldn't find any message queues building up. So that wasn't the problem ever. So we ruled out networking and disk. Networking we fixed, ruled out disk. Those are the 2 metrics that are comparatively the biggest impact on performance, as they are the slowest relative to the CPU. Looking at that hierarchy, we should look at RAM next, but there was nothing to show that RAM was leaking, used excessively, that there was garbage collection running too much, or none of this was happening. And all the while, the CPU utilization was at about 5% of the entire cluster. So nothing was maxed out. So we had to look at what the benchmark was actually doing in a little bit more detail. This is where we're going into HTTP request tracing. At this point, we went back to look at how exactly the observations of the benchmark were coming to us. So at the highest level, we found we could show the increased latency in a call to CouchDB's DB's info endpoint. This is an endpoint that gives you statistics about all the databases in your system, number of documents, file sizes, all of this, but it has to aggregate this from all the shards. So this does an operation for all databases in the system and has to do it 60 times each for one shard, one for each shard. So it's another one of those really expensive operations. And that showed similar behavior to what we were seeing in the benchmark. This is, again, on my local machine, redirecting the output elsewhere. The runtime is about half a second here. The more experience, we're using time and curl for this. Time is just a utility that starts another program and then counts how long it takes to exit. And the more experienced among you will start come with the pitchforks and say you can't use time for benchmarking. It's very imprecise because, well, time forks a new process, then launches curl. That's a lot of operating system machinery that has to run before the with the actual work is happening that we want to measure. But in comparison, for us just listing a directory with 5 files in them takes 4 milliseconds. And that doesn't make any difference to the 500 milliseconds we were looking at. So even with networking on the same machine, time is fine for benchmarking here. To understand a little bit better what's going on with the request, we'll have to briefly look at the layer cake of CouchDB. There's a lot of jargon. I'll explain it all. Requests come in at the top into a library called MochiWeb that accepts TCP requests, turns them into HTTP requests, hands them off to CHTTPD. CHTTPD will route things to the specific submodules, then uses another module called Fabric that itself uses Rexy to do these cross-cluster requests, like all the arrows you saw earlier. And then the end of that will talk to the actual internal CouchDB thing, Couch server to talk to the database, Couch index server to make a dynamic query, Couch config to get configuration out of the system, and so on. And then finally, when this all goes backwards, CHTTP sends the JSON back to the client via MochiWeb as well. This is what curl has a really cool feature called trace time. So if you run curl with -v --trace -time, you get curl output with microsecond resolution timestamps. I'll break this out in a second. This is a lot to read. But what you can see here is that half of the page is connecting to CouchDB, sending request headers, request completely sent off. This is when we start waiting for CouchDB. Response header, response status comes back, response headers come back, and then we get the response body. This is summing all this up a little bit. Receiving the request, the first bit of the diagram you just saw, or the printout you saw, 2.4 milliseconds. I have the exact numbers on the slide. Don't bother doing the math. Sending the response headers after the request was received, 3.5 milliseconds. And then sending, oopsie, that was one too many. Sending the response body, 0.5 millisecond. Again, this is just on my development machine. We can see that just sending a tiny body back didn't take a lot of time. Now let's run the same thing again on the production cluster, but without the benchmark, like in idle state. Receiving the request, 2 milliseconds, totally similar. Sending the response headers back is 10 milliseconds, totally fine also. Well, not totally fine, but fine enough. And then sending the response body about half a second, which now, given that it needs to talk to 60 shards instead of just 2, like on my machine, is kind of the increase that we were expecting with the work that was happening. Sorry, half a second here. Now, when we ran the benchmark and tried the same thing again, we came to these numbers. Receiving the request took about 4 milliseconds, that's twice as much, but with the 3,000 requests in parallel hammering the server, double requests, receive time seemed to be fine. Sending the response headers was a 10x increase, 100 milliseconds. That was a lot slower. That was a surprise. And then sending the response body back took 1.2 seconds, 24x slowdown. And then from this, we were somewhat expecting the response body to be slow because that was easily observable, but we saw that sending response headers back already was 10x slow, and we did not expect that. The way the endpoint, the DB's info endpoint works in CouchDB is the request comes in, gets accepted, and then CouchDB returns the response headers right away, and then does all the internal cluster work before returning the body. So we were thinking that's where all the time went, but we saw in between accepting and responding with response headers, we had a 100 millisecond delay, and that didn't match our understanding of how far anything worked. So did we find 2 bottlenecks, one when accepting new requests and one when collecting response body data from the many shards. To validate the hypothesis, we tried a different CouchDB endpoint that would do all the request stuff, but then read something out of memory from a single node. Reading from memory should be fast, not talking to the network should be fast, and so on. If we could see the same slowdown there, and we used the config API for this, that would validate our hypothesis. So without the benchmark, accepting new requests, collecting, oh no, these are the bottlenecks. So running the config query here, we get like 9 millisecond response time, and with the benchmark timing 132, 14x increase. It's a lot slower. So even just reading something out of memory, this should be instant. So we had validated, we had 2 bottlenecks that we had to deal with. So to look at how we solve those, we have to dive even deeper into the networking stack, it seemed. As we said earlier, CouchDB uses MochiWeb, and we had to look at, for doing TCP handling, and we had to look at the MochiWeb configuration for this. This is the CouchDB defaults, what the customer was also running at the time. There's 2 settings here. Backlog is an option that's passed to the TCP stack of the operating system that tells you how many connections can queue up before you reject new requests coming in. This is another inbox type queue that ideally has very low numbers, but in practice is a good trade-off between you not accepting new requests and a little bit of latency for the requests that are in flight when the server hits a sudden spike. It's a very useful feature. As far as we could tell, there were no dropped connections, so we never exceeded this backlog, but we wanted to see anyway just to make sure. So Linux comes with a tool that is called socket statistics. We used it in a while loop to dump out the current state of CouchDB port 5984. The send queue tells us the backlog setting, and the receive queue is the dynamic thing that goes up and down. Whatever we tried, we couldn't get it to reach the 128 queue limit, which was expected. We didn't see any rejected request. But we sometimes saw the receive queue into the 40s and 60s, grow into the 40s and 60s, but never for very long. We also tried setting the backlog to 256, but that didn't make any difference, just to make sure that our half-second sampling here wasn't missing anything. The other setting, however, is accepted pool size. This is a MochiWeb setting that defines the number of Erlang processes, remember they're lightweight, that can handle the accepting of new requests. The default is 16. That means there are 16 processes that can use at most 16 CPUs out of the hundreds we have per node to accept new TCP connections that are coming in one at a time. At that point in our career with doing CouchDB stuff since 2007, we had never a reason to change this ever. But we tried increasing it, we doubled it, and we did see a difference. Before I show you what, I want to talk to you a little bit about how to do benchmarking and config changes. The golden rule is make one change at a time. It might seem so tedious if you're in a hurry, but if you make more than one change, you never know what the interactions between 2 or more config changes actually give you. And then your measurements are out of whack. It's really not worth doing. For integer values, we recommend going 2x or 10x, depending on the value and the absolute values of those numbers, or go 1/2 or 1/10 if you want to go backwards. If you make changes and you see a difference, keep going to eventually see if there's more gains to be had or things get worse again. And once you hit your theoretical high point, go back a half step to find that local maximum that you're trying to find. Run your benchmark tests many times to repeat them, to rule out any statistical issues or any ghosts in the system that you might have. And then for good measure, at the end, revert to make sure you see the old behavior again, so that you not make any permanent, if you haven't filled up a cache somewhere, that makes your things faster from now on. So we made the 2x change to the accepted pool size, set it to 32, ran the benchmark again, and we ran a while loop with socket stats again and noticed slightly higher queue levels than before, but still no exceeding 128. But the biggest difference we saw that the response headers went from 100 milliseconds or 10x over the baseline, went down to 12 milliseconds, 1.2. That was very nice to see. We found the next bottleneck, the number of processes that could accept TCP requests. The very dumb brute force AB sending new requests at 3,000 per second, or 3,000 at a time, exceeded the capacity of the 16 processes per node. the 20% higher accept latency is entirely acceptable for the requests that were coming in. This was great. The final thing that the default change from 16 to 32 processes is now a CouchDB default. If you don't have that many CPUs, that won't be that many anyway. But if you're in the very high CPU configuration situation, you're benefiting from this now as well for free. So the last thing we had to look at is the DB's info thing that had the 12-second response time. One of the things we haven't really looked at for understanding things a little bit better is CPU utilization. And I've talked about how Erlang processes work a little bit, about how they run on schedulers, but it was time to get a proper picture of how that actually looked like. Modern Erlang comes with a thing that you can inspect its scheduler states, kind of like top for all the schedulers in the system. It's called microstate accounting, and it's time for black slides again here. This is how you invoke it: msacc start, run sample for 10 seconds, and then print out the stats, and also give us some system stats on top. The response is a bit unwieldy. We have different types of schedulers: dirty CPUs, dirty IO scheduler, and then at the end schedulers. This is again from my dev machine. Like this is one for 3 rows, one per type of scheduler per CPU. So my dev machine has 14 CPUs with 192 CPUs. This would like scroll a while the talk would be over by the time we're done. The most interesting thing for now is the bottom is the aggregate of all of those. So we have just regular schedulers, the one that I showed you, explained to you already with where the processes live. There's dirty CPU schedulers for native code. CouchDB uses native code for JSON parsing, for example. So that's why that's used. And then dirty IO schedulers are for when those native code bits need to do a schedule IO. So that's why we have 3 different types here. We see in this scenario, except for the sleep column, we have nothing that seemed like any of these types have more than like what weren't approaching exhaustion 100%. Sleep is fine because that just means they're idle. But also to double check even if the aggregate wouldn't show us 100% usage of one of those, we can look at the individual schedulers, but even those, none of them, they're all basically idle again. And again, this is my development machine doing nothing, so it's no surprise that there's nothing happening. But for the benchmark system, it was just the same. We couldn't get it to show at all that there was any CPU contention anywhere there, which is good. CouchDB has been programmed the correct way to do highly concurrent programming. That's good to know, but this can always happen, and this is how you find out. This was disappointing. Was important to rule out, but we were also a bit in the pickle. We already found and removed networking bottlenecks. TCP request accept bottleneck, we ruled out disk memory and CPU. What's left? We shared what we knew with the CouchDB development team. We're a very tight-knit community, and they helped us out a little bit, thanks to Nick from the team who pointed us in the right direction. There is another thing that you can tune when you deal with Erlang systems. And especially here, we're talking about the internal networking interface. Cutting this a little bit short because of time, but there's a network where you can each node can talk to all of the other nodes. And it's very easy from the programming point of view, and the VM abstracts that all away from you. You only see function calls and or get your functions called through this interface, but the VM does all the nitty-gritty networking bits of this. But of course, you can tune this. So by default, Erlang is using 60 megabytes message buffer for sending messages back and forth. And then these connections also have TCP socket options, and they have buffers, and those were 4 megabytes. We increased those. They have very funky names. Erlang is a very fun ecosystem. If you ever want to learn what CDBBL means, please come talk to us. Talk to me. The customer actually played with this, but that was before we made any of the other changes, so it didn't show up as a solution. But after we fixed all the other things, this became actually the next bottleneck. So the combination of all of these gave us the final push to the situation that we wanted. So with these changes, we still had the system under benchmark 4 millisecond requesting the accepting the request was totally fine. With this, we were still at the 12 millisecond response time for the aggregate requests, and then sending the response body back dropped from 1200 milliseconds or 1.2 seconds to about a second, half a second to a second. So there's a 2.4 increase, which again, given we're serving 3,000 and more requests per second, is totally fine. So in the end, our gut instinct from the beginning that all these errors might be the problem were all the problem. We looked at all the other things as well, just to make sure. But this was actually just 3 networking problems wrapped into one. That was a thing that I just glanced over in the beginning. The original benchmark showed about 6,000 requests per second. We got an easily sustained 25,000 requests per second, or 4x increase, which is in line with the nodes are 3 times bigger and we have another node. But in certain configurations, we got this up to 60,000 requests per second. And that's 10x, which I promised at the beginning, and it's absolutely not a lie. This is a real benchmark from Datadog, or a real graph from Datadog. All this was happening with 60 to 70% CPU utilization, which is exactly what you want. You have a little bit of headroom towards the limit of 80%. And we already knew this was the worst case scenario here. So having a little bit of buffer has served us very well. So this brings me to my end. We learned about network throughput, how to do benchmarking, how to find disk I/O issues, how Erlang processes work, how their inboxes work, and how you can measure those. We learned about HTTP request tracing, TCP accept handling, CPU utilization and process scheduling, and Erlang network messaging. And eventually, we managed to get a 10x increase. That is the end of my talk. Thank you very much. Thanks for coming. And yeah, talk to me in the breaks if you have any questions.
Thank you very much, Jan. Thank you. Round of applause.